So now we're going to figure out how to set up electric potentials. So if we go back to the last little things I was doing about moving down hills. So a different way you could explain this, and especially since I drew lines, is this could be a sheet of charge and another sheet of charge. This one's positive, this one's negative, or this one's positive, this one's less positive. However you want to think of it. So we're going to do that. But again, I want to go back a step. Electric force is equal to absolute value, okay, Q1, Q2, over R squared. Electric field was defined from electric force divided by the potential, excuse me, the test charge. And then we came up with the electric field for a point charge. And that's pretty easy to get. You just take this equation and divide by this equation. So you get KQ over R squared. We again do put absolute value around it. So last time I showed you the equation for the electric potential energy of a collection of point charges. So KQ1, Q2 over R, no square. And then we defined electric potential as the change in potential energy divided by a test charge. So if we just divide this by a test charge, we get the potential function for a point charge, and it's KQ over R. So compare and contrast, not squared, not absolute value. This potential can be positive or negative based upon whether the charge setting it up is positive or negative. So to connect these two, I want to show you, again, we're going to start from potential energy. Change in potential is defined as the negative work done by something. So now if I write that as delta U equals negative FDR, negative integral FDR, excuse me, I'm going to divide both sides by Q naught, just for the fun of it. Okay, and because it's a constant, I can put it inside or outside the integral, however you want to do it. Well, change in potential energy is divided by the test charge is delta V. Force divided by a test charge is electric field. So this is a negative integral of electric field, and there's a cosine angle in here. So we have two things we get from this. You can either, if you know the electric field, you can integrate it to find the potential function, or you can go backwards. So if you're looking for the electric field, we need to get rid of this integral. Well, the opposite of the integral is the derivative. So the electric field is the negative derivative of the potential function. So to show that this works, let's start from this potential function that was pretty easy to get for a point charge. So if V equals KQ over R, then E must equal negative derivative with respect to R of KQ over R. So again, I don't like dealing with variables in the denominator, so I'm going to rewrite. I need to do the negative derivative of KQ times R to the negative 1 power. So I have negative, and then I take the derivative of this. So remember, for derivatives, you bring down in the front the constant, so negative 1 times KQ, and then drop this by 1 power, so R to the negative 2. Well, these two negatives cancel, and then if I move R to the negative 2 back to the bottom, oh look, E equals KQ over R squared. Well, of course it does. We already knew this, but this is a nice, simple, connection showing that this is true. And we could start from this one and get back to this one. Of course, that's how we got potential energy in the first place. So two comments I want to make about this electric field equation. Electric field being the derivative of the potential equation. So the first thing I want you to notice is units. The unit of potential is the volt. The unit of distance is the meter. But electric field is in newtons per coulomb. These two units are equivalent. You will see electric fields quoted as 3,000 newtons per coulomb and 3,000 volts per meter. And this shows why these units are the same. The other thing is, if you have a uniform field, and this would be set up by two plates. So this would be two infinite plates with opposite charges. So if this one was positively charged and this one was negatively charged, you know the electric field would go positive to negative. So you'd get a nice uniform field. Well, this equation says the field is the negative potential difference divided by the distance between the two. I just chose to use x there. So the way we actually physically set this up, it would be very difficult to use friction to charge these two plates, but we could attach a battery to it with a potential difference. So if we attach a battery with the positive side to this plate and the negative side to this plate, and we make this a 10-volt battery, then the distance between the plates of, let's say, it's usually much smaller than is shown here. So like 0.02, I was going for millimeters, but if that's meter, let me just write it, 2 millimeters. So the electric field would have a strength of, so I can drop the negative sign because that tells you the opposite direction, it would have a strength of 10 divided by 0.002, 5,000 volts per meter, or 5,000 newtons per coulomb. So that's how you make electric fields in the real world. You use batteries to produce a potential difference, and then the electric field goes from the high side of the plate to the low side of the plate, because that ends up being the positive and the negative. By the way, you can put any two numbers here. In the previous video, I used 15 and 5. This side just needs to be higher than this side by 10. This is a 10-volt difference. That's what's set up by the battery. So if you connect this to ground, so this is 0, this would be 10, or this could be 5 and 15, or this can be 90 and 100. It can be any two numbers you feel like, as long as they're 10 apart and this one is higher. So that's it for this one. The next thing we're going to do is talk more about drawing electric fields based on the potential, and then what this applies to conductors.